Hi students, in this tutorial session, I will be solving problems from combinatorics that is covered in lecture 1, 2, 3. Here is the problem 1. Let S is a set consisting of numbers 1, 2, 3, so on n. Determine the number of towers of the form phi subset of A subset of B subset of S. This is our tower. Here S and phi fixed. Here we are free to change A and B. So the number of towers like this will be same as number of ways picking two subsets of S, A and B, where A is subset of B. Okay, so that means if I say C is set consisting of order pairs like a B, A, where A is subset of B, B is subset of S. That means simply A and B are subsets of S, where A is subset of B. Okay, we are interested in the number of elements in C. Okay, so first of all, I'm going to classify elements of C like this. Okay, so let me define CK as all like this. BA, okay, where phi subset of A subset of B subset of S. Further, the number of elements in B equal to K. Simply, we are collecting this order pair of subsets of S, B and A like this. Here A is subset of B, but B size is K. We are fixing size of B to be K. So K can be anything from 0, 1 to so on n. Fine. Okay, then we can easily see that the C will be union of these things. Okay, because if you take any candidate from C, B will have some size K from 0 to n. So that candidate will be sitting in corresponding CK, right? Okay, here we can also see easily Ci intersection Cj equal to Mt for I not equal to J. Okay, now we can see that by some rule the number of elements in C going to be summation k equal to 0 to n number of elements in Ck. Okay, now question is, what is the size of Ck? What is Ck here? All order pairs B and A, where A and B are subsets of S and A subset of B and size of B equal to K. Now here B is a subset of S with a size K. Okay, so to pick this order pair B and A, first we have to pick B, then we have to pick A, where A should be subset of B. Okay, how many ways we can choose B? Here B size should be K. Here S having n elements, we want to choose a subset of S with a size K. So first B can be chosen in n choose K ways, because number of subsets of size K for set with n elements will be n choose K. Okay, this many ways we can pick B. Once you pick B, then we can pick A in 2 to the power of K ways, because A should be subset of B. B having K elements. If B has a K elements, the number of subsets of B will be 2 to the power of K. So A can be any one of the subsets. That's why the number of elements in Ck is going to be n choose K times 2 to the power of K. Here K equal to 0, 1, 2, so on n. Okay, so the number of elements in C going to be summation K equal to 0 to n, n choose K times 2 to the power of K. By binomial theorem, this we can write 1 plus 2 all to the power of n. So this is going to be 3 to the power of n. So therefore, the answer is 3 to the power of n. So the number of towers of this form will be 3 to the power of n, since binomial theorem. Okay, Fine. Next, problem 2. There is even number 2n of people at party and they talk together in pairs with everyone. So, in pairs, in how many different ways can the 2n people be talking like this? Okay. Here pair means group of two people, right? Okay, so we are simply asking how many ways we can divide these 2n people into n groups of size 2, 2, 2, so on to each group of size 2. And these groups are going to be unlabeled, right? We have a formula for number of ways dividing n object into k groups of size n1, n2, so on, nk. The formula is this: n factorial by n1 factorial, n2 factorial, so on, nk factorial. When the groups are labeled, like a group 1, group 2, so on, group k. Okay. If the groups are unlabeled but still the sizes are different, implicitly those groups will be labeled by sizes. So there is no ambiguity. But when there are unlabeled groups but some sizes here same, for example, let us say n1 equal to n2 equal to n3. In that case, we will have overcount. To fix that, we have to divide, like 3 factorial. Okay, I mentioned these results in notes. Okay, so here we have a okay here we have 2n people and we have to divide them into n groups of size 2, 2, 2. All groups of same size. These are unlabeled groups. So here, if we apply the formula for unlabeled groups, we will have this 2n factorial by 2 factorial times 2 factorial times so on 2 factorial. This is n times. Okay, since these n groups are same size 2, so we will have overcount. To fix that, we need to divide by n factorial. Okay, the number of groups of equal size, right? Fine. So this is going to be the answer: 2n factorial by n factorial times 2 factorial to the power of n. Fine. Okay. Next, problem 3. Now suppose there is odd number 2n plus 1 of people at the party with everyone but one person talking with someone. How many different pairings are possible? Okay. Again, the problem is similar. This time we have to divide these 2n plus 1 people into n plus 1 groups of size 2, 2, 2, 2 and 1. Okay, n groups of size 2 and 1 group of size 1. Okay, so again, how many ways we can do that? 2n plus 1 factorial by 2 factorial, 2 factorial, so on, 2 factorial and 1 factorial. This is n times, okay, n groups of size 2 and 1 group of size 1. Okay, again here we have a n groups of same size 2. Okay, so we will have overcount. So to fix that, we need to divide by n factorial. Okay, number of equal sizes, that is n, right? Okay, so the answer will be 2n plus 1 factorial by n factorial 2 factorial to the power of n. We don't have to write 1 factorial, right? Fine. This is the answer. Fine. Next, problem 4. In how many ways can 12 indistinguishable apples and 1 orange be distributed among 3 children in such a way that each child gets at least 1 fruit? Okay, here 12 indistinguishable apples, that means 12 identical apples and 1 orange. There are 13 fruits. We need to distribute these 13 fruits among 3 children in a way that each child get at least 1 fruit. Okay, fine. Okay, here Here apples are indistinguishable, that means they look identical. So here there is no question of which child get which apples. Only question is how many apples each child getting. That's going to be matter. So let's say we have three childs with the names A, B, C. Okay. Let here x1 denote the number of apples A getting, x2 denote the number of apples B getting, x3 denote the number of apples C getting. Okay. Here number of apples only, right? That means apples are 12. So here x1 plus x2 plus x3 should be 12 because we have 12 indistinguishable apples. Okay, now what about orange? We can give orange to any one of the children. So let's say, let me do one case here. First, let's say we are giving orange to A. Okay, let's count how many ways we can distribute these fruits such that each child get at least one fruit. Okay, similarly, once you're done with this count, similarly we can do for the other case where orange is going to B, similarly with orange going to C. Okay, now here what we want, each child should get at least one fruit. A already got orange, so the number of apples he is going to get should be non-negative. It can be 0 also. So here x1 should be non-negative. B haven't got any orange, so the number of apples he is getting must be positive because each child should get at least one fruit, right? That's why x2 should be positive and x3 also should be positive. The same reason, right? Now we have to find the integer solution for this equation x1 plus x2 plus x3 equals 12, where x1 is non-negative, x2 positive, x3 positive. But we have a formula for non-negative integer solutions or positive integer solution. Okay, that's why we need to convert this equation into either in the form positive integer solution or non-negative integer solution, right? So what we do, so let me take the transformation here. Y1 equal to x1 plus 1. Okay, y2 same as x2, y3 same as x3. Okay, so now since x1 is non-negative, x1 plus 1 going to be positive, so y1 is going to be positive now. So this implies x1 will be what? Y1 minus 1. Fine. Okay, now if you change x1, x2, x3 in terms of y1, y2, y3, we end up with this equation: y1 minus 1 plus y2 plus y3 equal to 12. Okay, that implies y1 plus y2 plus y3 equal to 13 if you take minus 1 this side. Here y1 positive, y2 positive, y3 positive. We have a formula for positive integer solution of this type of equation: x1 plus x2 plus so on x are equal to n. Positive integer solutions are n minus 1, choose r minus 1. This is a positive integer solution. Non-negative integer solution formula is n plus r minus 1, choose r minus 1. I hope you remember. Okay, so here we want positive integer solutions of y1 plus y2 plus y3 equal to 13. Here the role of r played by 3, role of n played by 13. So the answer will be 13 minus 1, choose 3 minus 1, that would be 12, choose 2. Okay, 12 choose 2 only for case A getting orange. Similarly, for case B getting orange also same 12 choose 2. Similarly, for C getting orange also will be 12 choose 2. So in each distribution, orange will go to either A or B or C, right? So by some rule, we have to add up. The answer is going to be 12 choose 2 plus 12 choose 2 plus 12 choose 2. That is 3 times 12 choose 2. This is the answer. This many ways we can distribute these 12 indistinguishable apples and 1 orange to 3 children in a way each child get at least 1 fruit. Fine. Next, problem 5. There are 2n plus 1 identical books to be put in bookcase with a 3 shelves. In how many ways can this be done if each pair of shelves together contain more than other shelf? Okay, here there are 3 shelves. Okay, let me draw something like this. Here 3 shelves. Okay, so here 2n plus 1 identical books. Okay, so we don't ask like which books are going to shelf 1. Okay, all books are identical, right? So no meaning. So we can only be interested in how many books we are putting in shelf 1. Okay, that's all going to be matter because all books are identical. Okay, let here x1 denote the number of books that are going to shelf 1, x2 denote the number of books that are going to shelf 2, x3 going to be number of books that are going to shelf 3. Here x1 plus x2 plus x3 should be equal to 2n plus 1. Okay, what is our condition here? Each pair of shelves together contain more than other shelves. That means total books in any two shelves should be more than books in other shelf. That means here the conditions are going to be x1 plus x2 should be bigger than x3 and x1 plus x3 should be bigger than x2 and x2 plus x3 should be bigger than x1. Okay, so we are interested in non-negative integer solutions of this equation that satisfying all these conditions. X1 plus x2 greater than x3, x1 plus x3 greater than x2, x2 plus x3 greater than x1. Okay, fine. So if you try to count directly with this, it's going to be a little bit difficult. Here we are going to use complementation principle, okay, or you can say subtraction principle. Okay, what we are not interested, if one of the condition fails, then we are not interested, right? So what will be the negation of this? If you apply the negation for this condition, we will have x1 plus x2 less than or equal to x3, x1 plus x3 or end will become r when you apply negation, x1 plus x3 less than or equal to x2 or x2 plus x3 less than or equal to x1. Okay, since we have an odd number of books, so equality case will not happen. If x1 plus x2 equal to x3, then x1 plus x2 plus x3 will be even, but that is not the case. So we can eliminate this equal case here. Okay, fine. Okay, so if one of these condition is true, if x1 plus x2 less than x3 or x1 plus x3 less than x2 or x2 plus x3 less than x1, then we don't like that distribution, right? Okay, so this is what we are not interested in. Okay, now what we do, let's count total way of arranging these 2n plus 1 books into 3 shelves without any condition. Then we subtract the distribution that we don't like using subtraction principle. Then we get the count for what we want. Okay, first of all, total ways of distributing these 2n plus 1 books into these 3 shelves going to be what? x1 plus x2 plus x3 equal to 2n plus 1. Okay, no condition, simply there should be non-negative for I equal to 1, 2, 3. Simply non-negative integer solution of this equation, that is going to be 2n plus 1 plus 3 minus 1, choose 3 minus 1, that equal to 2n plus 3, choose 2. This is the total, okay, total count. Now, what is the count of the distribution that we are not interested in? So, all non-negative integer solutions with which satisfy one of these three conditions we don't like, right? Now, I can say that these three conditions equivalent to saying that at least one of the shelf containing n plus 1 or more, because I can say that, for example, x1 plus x2 less than x3 means what? What we know here, x1 plus x2 plus x3 equal to 2n plus 1. If x1 plus x2 less than x3, then we can say that, so we can say that this x1 plus x2 plus x3 will be less than x3 plus x3, okay, but this is actually equal to what? 2n plus 1. So 2n plus 1 less than 2x3. That implies x3 will be greater than or equal to n plus 1. Okay, so this condition is equivalent to saying that x3 greater than or equal to n plus 1. This condition will be equivalent to saying that x2 greater than or equal to n plus 1. This condition will be equivalent to saying that x1 greater than or equal to n plus 1. So this condition will be equivalent to saying that at least one shelf containing n plus 1 or more. Okay, so let me rewrite. So distribution that we don't like come from the equation like this: x1 plus x2 plus x3 equal to 2n plus 1, either x1 greater than or equal to n plus 1 or x2 greater than or equal to n plus 1 or x3 greater than or equal to n plus 1. Okay, let's do each case separately. First for x1 greater than or equal to n plus 1, then x2 non-negative, x3 non-negative. Similarly, for x2 greater than or equal to n plus 1, x1 non-negative, x2 non-negative. Similarly, for x3 greater than or equal to n plus 1, x1 non-negative, x2 non-negative. Okay, we count each three separately, then we can add up by sum rule. Okay, so first let me do for case 1. Okay, x1 plus x2 plus x3 equal to 2n plus 1 and x1 greater than or equal to n plus 1 and x2 non-negative, x3 non-negative. See, when I say or here, exclusive sense, because two things cannot happen. We can't see like x1 greater than or equal to n plus 1 and x2 also greater than or equal to n plus 1. Then the total books will be more than 2n plus 2. That is not the case here. So we can say that only one of them happen. Okay, not more than that. That's why one case is going to be this: x1 greater than or equal to n plus 1, x2 greater than or equal to 0, x3 greater than or equal to 0. Okay, now to find the non-negative integer solution for this equation, let us convert this problem into non-negative integer solution. For that, let me use the transformation y1 equal to x1 minus of n plus 1, y2 same as x2, y3 same as x3. Okay, now here since x1 greater than or equal to n plus 1, we can say that here y1 is non-negative. Okay, so this is going to be non-negative. Okay, anyway, these are always non-negative anyway. Okay, now this implies x1 is going to be what? Y1 plus n plus 1. Okay, fine. Now if we convert this equation in terms of y1, y2, y3, it will be this: y1 plus n plus 1 plus y2 plus y3 equal to 2n plus 1. Okay, now if I take n plus 1 that side, I will have y1 plus y2 plus y3 equal to n. Here y1 non-negative, y2 non-negative, y3 non-negative. Now here we are interested in non-negative integer solutions of this equation. So it's going to be n plus 3 minus 1, choose 3 minus 1, that is n plus 2, choose 2. This is the count for this equation. Similarly, for other condition, when x1 greater than or equal 0, x2 greater than or equal to n plus 1, x3 greater than or equal 0 also, we will have same count n plus 2, choose 2. Okay, so that's why I can say that x1 plus x2 plus x3 equal to 2n plus 1, and x1 greater than or equal to n plus 1, or x2 greater than or equal to n plus 1, or x3 greater than or equal to n plus 1. The count is going to be 3 times this. So the number of solutions going to be 3 times n plus 2, choose 2. Okay, now we got the count for the non-negative integer solution that we don't like, and we also got the count for the total solution. So now, using complementation principle, we can say that the number of integer solutions of x1 plus x2 plus x3 equal to 2n plus 1, where x1 greater than x1 plus x2 greater than x3, and x1 plus x3 greater than x2, and x2 plus x3 greater than x1 is going to be what? Total, that is 2n plus 3, choose 2, minus 3 times n plus 2, choose 2. Okay, 2n plus 1 identical books among 3 shelves in a way that total books in any 2 shelves will be more than other shelf. Fine. Okay, next problem 6. Determine a general formula for the number of permutations of the set 1, 2, 3, so on n, in which exactly k are in their natural position. K is anything from 0 to n. Okay, so here we want exactly k of 1 to n should be fixed and remaining should not be fixed. Okay, so which k? Okay, first of all, we need to pick k position out of n position. We need to fix them, and remaining position must be disturbed. That means we need to make sure remaining position nothing takes their own place. Okay, so first of all, we need to pick k position from n, so that can be done n choose k ways. Okay, then we have to fix them. That can be done one way. Okay, then remaining n minus k position, then in remaining n minus k position we have to shuffle in a way that nothing should take their own place. That means we want them to be derangements. How many derangements are possible with n minus k objects? That is dn minus k. Okay, so simply the answer going to be n choose k times dn minus k. Okay, so this many ways we can make a permutations of the set 1 to so on n in which exactly k are fixed, remaining n minus k are not fixed. Okay, fine. Next, problem 7. In how many ways a teacher can distribute the 30 response sheet to the 30 students so that at least one student receives his or her own response sheet? Okay, I'm simply tweaking the problem that I discussed in the video. Okay, so first of all, the total distribution is going to be 30 factorial because simply like a permutations of 30 objects, from which we are going to subtract the number of distributions in which no student receive their own response sheet. Okay, so that's going to be simply derangements. That will be d30. Okay, this is going to be answer 30 factorial minus d30. Total distributions are 30 factorial. The distribution that we don't like are d30. Okay, so by subtraction principle or complementation principle, we can say that answer is 30 factorial minus d30. Fine. Next, problem 8. Use the combinatorial reasoning to derive the identity n factorial equal to n choose 0 times dn plus n choose 1 times dn minus 1 plus n choose 2 times dn minus 2 so on n choose n minus 1 times d1 plus n choose n times d0. Okay. Okay, first of all, if I look at a left hand side n factorial, that can be seen as count of permutations of n objects. Let's say a equal to set consisting of n objects 1, 2, 3, so on n. Okay, so let us say S is going to be set of all permutations of A. The number of elements in S, we can immediately see n factorial. Okay, so these permutations, if you look at any permutation, you will see that some objects are fixed in original position, some are disturbed, right? So in any permutation, the number of objects fixed going to be vary from 0 to n, right? So let me classify this permutation like this. Sk is what? Set of permutations of A in which exactly k objects, that means k numbers from 1 to n are fixed exactly. Okay, so then the number of elements in Sk going to be what? So k objects, we already seen one problem. So first of all, we have to pick the k object. That can be done n choose k ways. Okay, we can fix any k object out of n. So once you're done that, then you can fix them in one way. Then the remaining n minus k position, okay, should be disturbed. That means they must form a derangement. So nothing should take their own place. So that's going to be dn minus k. So it's going to be n choose k times dn minus k for k equal to 0, 1, 2, so on n. Now we can easily see that S is going to be union of Sk, k vary from 0 to n. Here you can also see Si intersection Sj equal to mt for I not equal to j. So that means S0, S1, S2, so on, Sk form a partition. So by some rule we can write number of elements in S going to be summation k equal 0 to n number of elements in Sk. Okay. So the left hand side we know that is n factorial. The right hand side summation k equal to 0 to n. The count of Sk, the size of Sk going to be n choose k times dn minus k. Okay, so therefore n factorial is n choose 0 times dn plus n choose 1 times dn minus 1, n choose 2 times dn minus 2, and so on. N choose n minus 1 times d1, n choose n times d0. This is the identity. We have given combinatorial reasoning. So this is a combinatorial proof for this identity. Fine. Next, problem 9. How many ways can we arrange the letters of the word pepper on the grid shown right so that no row is empty? Okay. There are 4 rows as you can see. We want to arrange the letters of the word pepper so that no row is empty. Here in the pepper there are 6 letters, but in which 3 P's are identical, 2 E's are identical, 1 R is identical. Fine. Okay. First of all, let's get the total arrangement without any condition. So let S be the set of all arrangements of the letters of the word pepper on this grid. Okay, so what would be the size of S? In this grid, as you can see, there are 10 cells, 1 plus 2 plus 3 plus 4, in which we are to select 6 cells for the letters of the word pepper first. Let me pick 6. Then we are to arrange the letters of the word pepper in the selected 6 position. Okay, so we can arrange them in 6 factorial by 3 factorial, 2 factorial, 1 factorial, because 3 P's are identical, 2 E's are identical, 1 R is identical. So this many ways we can arrange them in selected 6 positions. Okay, this is total count. So fine. Now let AI be the set of all arrangements in grid so that ith row is empty. For I equal to 1, 2, 3, 4. Fine. Okay. That means A1 is set of all arrangements in which row 1 is empty. A2 is the set of all arrangements in which row 2 is empty. A3 is the set of all arrangements in which row 3 is empty. A4 is set of all arrangements in which row 4 is empty. Okay, fine. But we are interested in arrangements in which no row is empty. That means we are precisely interested in arrangements from A1 complement intersection, A2 complement intersection, A3 complement intersection, A4 complement. Okay. Any arrangement sitting in this intersection will have no row empty, because any arrangement sitting here will be in A1 complement, that means first row is not empty, and also in A2 complement, that means second row is also not empty, also is sitting in A3 complement, that means third row is also not empty, and also sitting in A4 complement means fourth row is also not empty. That means no row is empty. So this is the precisely count we are interested in. So, but we can write down the number of elements in A1 complement intersection, A2 complement intersection, A3 complement intersection, A4 complement. I can write the total number of elements in S minus number of elements in A1 union, A2 union, A3 union, A4. Okay. Here I can apply principle of inclusion and exclusion. Okay, and now the number of elements in S. Here if I apply principle of inclusion exclusion, summation 1 less than or equal to I less than or equal to 4, number of elements in AI minus double summation number of elements in AI intersection AJ. Here 1 less than or equal to I less than j less than or equal to 4, then triple summation 1 less than or equal to I less than j less than k less than or equal to 4, number of elements in AI intersection AJ intersection AK, finally minus number of elements in A1 intersection A2 intersection A3 intersection A4. This is from formula of principle of inclusion exclusion. Okay, now we already know the number of elements in S. We got a count. Now let us see what is the number of elements in A1. So A1 is what? All arrangements in which row 1 is empty. If you want row 1 to be empty, don't use the row 1 at all. Then we have 9 cells. In 9 cells, we have to arrange 6 letters. So 9 choose 6. Again 6 factorial by 3 factorial, 2 factorial, 1 factorial. Similarly, number of elements in A2. If you want row 2 to be empty, don't use the row 2. Then we have 8 cells. So it's going to be 8 choose 6 times 6 factorial by 3 factorial, 2 factorial, 1 factorial. Similarly, A3, number of elements in A3. If you want row 3 to be empty, then don't use the row 3. Then we have 7 cells. So 7 choose 6 times 6 factorial by 3 factorial, 2 factorial, 1 factorial. And if you want number of elements in A4, that means if you want row 4 to be empty, don't use row 4. Then we have 6 choose 6 times 6 factorial by 3 factorial, 2 factorial, 1 factorial. Okay. Similarly, number of elements in A1 intersection A2. If you want row 1 and row 2 to be empty, then don't use row 1 and row 2. Then still you have 7 cells. So 7 choose 6, 6 factorial by 3 factorial, 2 factorial, 1 factorial. Number of elements in A1 intersection A3. If you want row 1 and row 3 to be empty, still we have 6 cells. So again 6 choose 6 times 6 factorial by 3 factorial, 2 factorial, 1 factorial. And if you want row 1 and row 4 to be empty, then we have only 5 cells left, so we cannot use 6 letters in 5 cells, so it's going to be 0. If you want row 2 and row 3 to be empty, again we cannot do that, 0. Similarly, if you want row 2 and row 4, same thing, 0. And number of elements in A3 intersection A4 also 0. And obviously number of elements in A1 intersection, A2 intersection, A3 intersection, A4 also will be 0 because we cannot make all of them to be empty. Okay, so now let's plug in all these values in the above expression. Number of elements in S is what? 10 choose 6 times 6 factorial by 3 factorial, 2 factorial, 1 factorial minus summation. Here we have a number of elements in A1, that is 9 choose 6. 6 factorial by 3 factorial, 2 factorial, 1 factorial. Number of elements in A2, that is 8 choose 6. 6 factorial by 3 factorial, 2 factorial, 1 factorial. Number of elements in A3, that is 7 choose 6. 6 factorial by 3 factorial, 2 factorial, 1 factorial. And the number of elements in A4, that is 6 choose 6. 6 factorial by 3 factorial, 2 factorial, 1 factorial. Okay, then minus number of elements in A1 intersection A2, that is going to be 7 choose 6 times 6 factorial, 3 factorial, 2 factorial, 1 factorial, minus number of elements in A1 intersection A3, that is 6 factorial, 6 choose 6 times 6 factorial by 3 factorial, 2 factorial, 1 factorial. And I forgot to mention here, all these triple combinations are also 0. Number of elements in A intersection AJ intersection AK going to be 0 for all 1 less than or equal to I less than J less than K less than or equal to 4. Okay, that's why from here onwards everything is 0. Okay, fine. So if you simplify this, you will get the required count. Okay, so that is number of elements in A1 complement intersection, A2 complement intersection, A3 complement intersection, A4. Okay, just try to see this thing. Okay, fine. Problem 10. Give a combinatorial proof of the identity summation k equal to 1 to n choose k times k square equal to 2 to the power of n minus 2 times n plus 1. We want to give a combinatorial proof to prove this identity. So we want to come up with a counting argument that shows left hand side same as right hand side. So our idea is to come up with a set of objects, and we want to count the set of objects in two different ways. One way of counting that set of objects should give the left hand side expression. Other way of counting the same set of objects should give the right hand side expression. Then we can say that the left hand side same as right hand side. Fine. Okay, so the set of objects that we are going to consider is following. So let's say there are n people. We want to select a group and we want to fill two positions out of that group. Okay, here the two positions can be given to same persons if we want. Okay, so here we want to select a group out of n people. That should be non-empty group because we need at least one person to fill these two positions, right? So we need a group, and out of that group we fill two positions. Okay, both can be given to same person if you want. Okay, so now let me count this set of objects in two different ways. Okay, first what we are doing, one way of counting this set of objects, that is selecting group from n people and filling two positions from selected group. Okay, fine. First of all, the group that we are selecting can have size from 1 to n, right? So first of all, if I say we are picking group of size k, then we can pick the group of size k from n people in n choose k ways. Okay, once you are done this, then you need to fill two positions from selected k people. Okay, so position 1, we can pick one person from k people. For position 2 also, still we have k choices because I told you that both positions can be given to same persons if you want. So that's why position 1 can be done in k chosen ways, position 2 also can be filled in k chosen ways. Okay. Now here k can be anything from 1 to n. Okay. So what we have here, summation k equal to 1 to n choose k times k square. This many ways we can select a group and filling two positions out of the selected group. Okay, summation k equal to 1 to n choose k times k square. Okay, now let us count the same set of objects in different way. Here, first we select people to fill that position, then we form the remaining group. There are two cases here. When we pick the people to fill the position, we may give two positions to single person or two positions to two different person. Okay, so let's do two cases. If we are choosing one, if we are picking one person to fill the two position, then we need only one person out of n people. First let us pick one person out of n people and let's assign two positions for this single person. That can be done only one way, right? Then we have to pick the remaining group. Okay, we want one group, right? That could be any subset of remaining n minus 1 people. So a set with n minus 1 elements will have 2 to the power of n minus 1 subset. So remaining group can be formed in 2 to the power of n minus 1 ways. Or so we may pick first two people to assign two positions. Okay, for position 1 we need a one person from n people. For position 2, from remaining n minus 1 people we pick one, because we are picking two different people for two different positions. Then we have to form the remaining group. Now we left with n minus 2 people, so there will be 2 to the power of n minus 2 subsets. Okay, so remaining group can be formed in 2 to the power of n minus 2 ways. Okay, now here n times 2 to the power of n minus 1 plus n times n minus 1 2 to the power of n minus 2. If I take n times 2 to the power of n minus 2 common, then we have 2 plus n minus 1. So this is n times now this is 2 to the power of n minus 2 times n plus 1. Therefore, we have summation k equal to 1 to n choose k times k square equal to 2 to the power of n minus 2 times n plus 1. Okay, this is the combinatorial reasoning to prove this identity. Okay. Next problem, problem 11. Give a combinatorial proof of the identity summation k equal to 1 to n choose k times k cube equal to 2 to the power of n minus 3 times n square times n plus 3. I will let you do this. This is going to be exercise. Okay. It's pretty similar to the previous one. Only thing is, instead of filling two positions, here you need to fill three positions, and three positions can be given to one people or two people or three people. Okay, so please do this. Okay, pretty similar to the previous one. Only thing is, here we are picking group and filling three positions out of the group. Here these three positions can be given to single person or any two person or any three person. Okay, from the selected group. Okay, just to, okay, you can do this. Okay, exercise. Next, problem 12. Fermat's identity. Prove that n choose k equal to summation I equal to k to n I minus 1 choose k minus 1. Here n greater than or equal to k. Okay, fine. So we want to come up with some counting argument that shows that left hand side same as right hand side. At least I am familiar with the left hand side expression n choose k, which usually count the number of subsets of size k from set with n objects. We also know that n choose k also count number of binary strings of length n with exactly k ones, right? Okay, let me consider that s equal to set of binary strings of length n with exactly k ones, remaining n minus k zeros. Okay, the number of elements in S is what we already know, that would be n choose k. At least I can recognize left hand side n choose k as count of binary strings of length n with exactly k ones. Okay, fine. Okay, if you look at any binary string of length n, okay, the position 1, 2, 3, so on n minus 1. Here let us say here we have a k. Okay, so if you are focusing on the last one in the binary string, the last one may occur at k. It never occur before k, right? Okay, because it has exactly k1, so the last one position will be at least start at k. It could be at k or k plus 1 or k plus 2, or it could be at n also. So let's classify all these binary strings in terms of the last position of 1. Okay, so now, so let us say Si is set of all binary strings of length n with exactly k ones, and last one occur at position I. Here I is going to be anything from k to n. Okay, so we cannot see last one before the k position because there are exactly k ones, right? Okay, fine. So that means, so in case of Si, let's say position 1, position 2, let us say this is position I and position n, like this. Okay, here in this case the last one occur at here, after that all will be 0. Okay, so now, so here the last one means kth one. Okay, there are exactly k ones, right? So remaining k minus 1 ones will be here. Okay, how many ways such strings can be made? The number of elements in Si going to be here, these are fixed, and ith position also fixed. Remaining I minus 1 position, okay, we should have exactly k minus 1 1. Okay, so this is going to be binary string of length I minus 1. Okay, let me, okay, this is going to be binary string of length I minus 1 with exactly k minus 1 ones. What is the count of that? I minus 1 choose k minus 1. Okay, remaining all fixed, so that can be done only one way. So here I is greater than or equal to k. Fine. Okay, also I can say here k less than or equal to I less than or equal to n. Fine. Here you can see that the OLS we can write as union of I equal to k to n Si. Also we can see Si intersection Sj equal to Mt for I not equal j. That means here Sk plus 1 so on Sn will form a partition for S. So the number of elements in S is going to be summation I equal to k to n number of elements in S side. That implies the left hand side number of elements in S we already know n choose k. The right hand side summation I equal to k to n number of elements in Si we just realize that is I minus 1 choose k minus 1. Okay, so this is Fermat's identity. Fine. Okay, let me stop. Thank you.